So what I want to do is go through some of the things that we talked about on Monday and Tuesday, just as a refresher here. So Monday, Tuesday, and I'll try to do one Friday morning for the Wednesday, Thursday stuff, and then the other ones were kind of on our own. So lesson one, we talked about basic network. What is a network? And we had perspective, whether we had like home users or home users or enterprise, and we're more concerned with the enterprise. And the networks that we talked about there were LAN, WAN, CAN, MAN, PAN, and wireless personal area networks. The local area network talked about a restricted area. One of the big differences between LAN and WAN, aside from the fact that the protocols are different at layer 2, is that in a LAN, a local area network, we normally own all of the wiring system. We own the entire network. We own the routers that might be in it, layer 3 switches, layer 2 switches, and the machines. When we get into a WAN, we're typically going to have to get a third party involved, from a leased line down to an internet provider that we would use our business cable modem account to do. And then we talked about topologies. We had the bus, ring, and mesh, and the true bus, everything saw everything else. That's not necessarily going to be the case because we talked about some ways to make that better. The device is the bus. The true bus devices that we talked about were the bus, the wired bus. Get my pencil going here. I know everybody loves it. Okay. Yeah. Exactly. Okay, so let's say that we have this bus here. That's exactly what a hub is. If we take this is the bus, everything, we got the T's down here, pretend there are T's here, connected here. If we draw a box around it, put it in a box, just like you said, and shrink it, we got a hub. And then it's a star, a physical star, and a logical bus. A ring, we can do the same thing. It's a little bit more complex, but we have and a ring, it just goes around in a circle, right? Goes the other way, but a ring actually goes this way. So it goes in one and out one, okay? Yes, no, maybe? Okay, what we have here, so we would have a ring in and a ring out connector, okay? Does that make sense? What we can do with it is we put these things in here, and we have 2 for each machine, and we have the ring in here and the ring out here. These 2 are connected, and this is the ring in, and I'm not going to keep going, and then the ring out. So when you do this, you're actually going in, ring out, going from one to the other. You've created the ring logical topology, but you have a physical star. Yes, but the advantage to a ring is they communicate with their nearest upstream neighbor, so that if they don't get something from this nearest upstream neighbor, there is a centralized machine, because you can always go in one direction. If you have a break here, we can keep going in this direction. We just can't go on around, right? It will report a problem with its nearest upstream neighbor, which assists in the troubleshooting. In a bus, if we had this thing, and these would be our T connectors here. Let's see if let's just say that we had, just pretend they're T connectors. If somebody comes in here and disconnects one of these things, this whole segment goes down. The ring, yep. Well, yeah. Computer, this one is 1. Computer 1 reports that, and this one's 4. So I'm not hearing from computer 4. It reports that. So you know about where to go to start troubleshooting. This one you have no idea. what you do is go to the midway point, put a T in, terminate it, and see which half of the network works. Once that happens, you keep doing a halving, divide and conquer sort of arrangement with that thing. Mm-hmm. Yeah. Yep. 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 Mm-hmm. Yeah. See. Yeah. 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 Exactly. These were the days before TDRs. My first experience with TDR was in the Navy when I worked on A4s, and when they would do engine work, they took it apart and they would break. I was an AT at the time, and they would break it in part and they would disconnect all of our cables. Obviously, they didn't always put them back together right, and they never told us, so we'd have to go and use a TDR to find out where they had screwed that up. Does anybody use the wireless fence for a dog? You guys don't have dogs, huh? Two cats. Well, what it is basically a run of wire that sends a signal around in a big circle back to the transmitter. If this thing goes down, where's the break? Because I used to have one that did that. Somewhere on that line, you go to the middle. I had a big long piece of wire. I go to the middle and I would bring it back and then connect it to this one and connect it to that one, and whichever one I got a resistance on, obviously not an infinite resistance on, was good and the other half was bad. So I put it back together and go to the halfway point of this and do the same thing. Divide and conquer. We don't really use these buses anymore. What we're using is switches, right? Now, what the disadvantage of here is a broadcast domain. Or actually, no, it's not. It's a collision domain and a broadcast domain. The whole thing's a collision domain. The whole thing here on the hub is a collision domain. One giant collision domain. By the way, Clifton, is who else supposed to be there? Dominic's here. Oh yeah, I got him. You're the only two guys. Dallas, because Rodney doesn't come in, right? He's not. Yeah, he's not a Chapter 33 guy. Anyhow, this is one giant collision domain, and that's what we wanted to get away from, and that's what switches do for us, and that's what we're going to start today with switches. Switches create a collision domain on each port. And I'm going to say sort of, because we'll talk about here the first time it comes through, we're going to look at MAC tables. First time a packet comes in, it doesn't know where it's going, so it goes out all of them, kind of like a collision domain. But after that, it makes this table. We talked about the MAC table that has the port and the MAC address, so that if it's going to MAC address A, it only sends it to MAC address A. Nobody else sees it. A big advantage. So it creates collision domains. The switch is still one giant broadcast domain, because the broadcast domain is routers. Routers stop the broadcast domains. So we had collision domains and broadcast domains. I guess that kind of worked into that one, didn't it? A hub, legacy device, that's what we're talking about up here with the one giant collision domain. One giant collision domain. Where it was, that was around here was my ugly hub with the everybody talking to everything else, where we took the bus and visualize it. Nobody has a problem visualizing everything connected to a piece of wire, I don't think. Piece of coax, what this is. Obviously not coax in here. We build a box around it and shrink it, so we actually have everything talking to everything else on the hub, legacy domain. Switch created collision domains, and the router was the broadcast domains. The OSI model, 7 layers. One of the focal points is the transport layer, layer 4, where we have UDP, and we'll get to those in just a second, and TCP here. And the UDP was the connectionless, and we looked at the header at one of those yesterday. It was pretty easy header. It had a source MAC, a destination MAC. Actually, the destination's going first, and then the data basically, and that was it. TCP had all that numbering system that went into it, and then the TCP IP model was the one where we combined things. The top three, what we combined was the top 3 layers, and then we used the bottom 2 layers were the network access. The top 3 layers of the OSI model became the application layer. Less the TCP and UDP. TCP, some protocols in TCP, HTTP, FTP, HTTPS, POP3, and it's supposed to be IMAP under there. Connection oriented, we had the 3-way handshake, the synchronization packet, the SYNAC, and then the ACK to establish a connection at layer 4. So these are layer 4 protocols, connection oriented. UDP, a couple of protocols that run there, DNS and DHCP run there, and this is the 4 layer. So here we have TCP, HTTP, FTP, Telnet, SMTP, POP3, IMAP, some others that I put in here. UDP, DNS, SNMP, TFTP, trivial file, NetBIOS. They didn't put DHCP in here, but I'll put DHCP on the drawing. TCP, UDP. Layer 3 protocols. Here we had ICMP, ping, ARP, and ARP was this is the way that we get our MAC address from the IP address. Reverse ARP goes the other way around. I know what my IP address is. I have no idea what my these are for diskless workstations. For the OSI, yeah. When you see layers, yeah, you're right, because this would be layer 1, layer 2, 3, and 4. Yeah, layer network, internetwork. How's that? Yes. And when you see numbers, they're typically, well, unlike me, they will typically going to talk about the OSI model. The reason I always do that is because when I learned this thing, there wasn't a TCP model. It came along a bit later. So we have these things. Yeah, layer 3 of the OSI we'll do over here, 3 of the OSI, and this will be 4 of the OSI, 3, whatever, and then 4, 5, 6, and 7 are here. 5 through 7, and then 4 over here, 1 and 2. And I'll go back to, yeah, the TCP model actually makes a whole lot more sense. But it's connectionless. Something else has to be responsible for delivery. And then we have down here the TCP 3-way handshakes. I did something with my slides this morning. There you go. To move this thing around, I moved all the other stuff the wrong way. But we'll go on to the next slide. So UDP, TNS, NTP, THCP, TFTP, connectionless protocol. In lesson 2, we talked about the devices, hub switches, and routers, and I think we've already kind of beaten them to death. We had the Cisco wireless solution, the universal wireless solution, the UWN, which had the wireless controllers and the lightweight access points that the controllers controlled or managed. Firewalls and access points. The firewalls allowed us to prevent users from somebody unwanted from getting into our network from outside, and then access points for the wireless. One of the disadvantages, and I know I take up time and probably not, disadvantages of wireless access points is we have our clever firewall here. I can't draw the bricks. And back here we have our wireless access point. That signal goes on the other side of the firewall. So these things got to be protected. These usually sit inside the firewall. That can be an issue. That can be a breach point if you think about it, because it goes around the firewall. The wireless stuff doesn't go through this firewall. So you need to protect those assets also. The Cisco 3-layer or 3-tier, and it's always something that Cisco loves their stuff the core distribution and access, and then the devices that are there. The access layer, not a really big deal. Layer 2 switches to have access to the network. The distribution layer were routers, and they went to our other sites. So those went to the sites. And then the core was the backbone, and it's where the high-speed layer 3 switches are. The purpose of this, the Cisco stated reliable, secure, scalable. Reliable, secure, and scalable. It's not going to be cheap. It's going to be reliable, secure, and scalable. And we also had the ability to have the collapsed core, where we basically had a layer 3 switch in here and then layer 2 switches. We did all the functionality at that layer 3 switch. Smaller networks would do that. And again, I told you that's basically what we wound up with our network. Each of the access devices were at the in the individual rooms. And then we talked about the iOS commands, and you've done some commands. Get into privilege exec mode. We use the enable command, config mode, config T. The user exec mode, the greater than sign where we start up, we looked at did the question mark for the help, and the question mark for the help is down there, tab to complete. Show space, question mark will show you the commands. I know we'll get back to this other thing. Config T, and then the configure the interface. We'll get into other things when we do routers. We'll do router, whatever the protocol is, router rep, router EIGRP, and then all the other necessities. Will put us in a specific configuration mode. Config T, and then interface whatever, interface 000 gets us into the config interface mode. Obviously, the config T is going to be executed at the privilege exec mode, not in the config, and then the interface will be executed at the other one. And then the commands that are available at those levels, the question mark, and the little, if you are at a level and you're trying to execute a command from a different level, the do command, do show, do whatever else, you can do that. The tab to complete a command, you've already seen my typos. I make lots of them. I get in too big of a hurry. Use the tab key in order to make that work for you, and then the question mark for the help. IPv4, we had our classes, the A, B, C, D, and E. We can use the A, B's, and C's, and we had our class full mask, which basically with the dotted DDN dotted decimal, the 255.0.0.0 for A's, 255.255.0.0 for the B's, and then the 255.255.255.0 for the C's, and that's it. If you see a 255.255.255.255, that's screening for an individual address. You might see that for a host address, but it's not going to be a network address. The subnet mask, the ones tell us how much of the address is network and how much is host. So the ones are network and the zeros are host, and they have to be contiguous ones. And then when we start with zeros, we have to continue with zeros. We talked about a socket. It's an IP address and a port number where we're going. And we have a socket for the destinations will be the well-known sockets or well-known port numbers. The origination sockets will be a random port number. Doesn't matter. Actually, they tend to be sequential. But when we do that, we have to have a socket at each end, the IP address, to actually make the sessions work. Subnetting, we use the increment number to find the network addresses as well as the subnet mask. The subnet mask was 256 minus the increment. Quick way to do that, or you can use the add up the numbers in the little table of that. Yeah, the mask 256. The mask equals 256 minus the increment. Lesson 3, we talked about the host table and a host file. The host table, I think you create one of those in the labs. The host file is something that's left over from the days when there were 4, 5, or 10 computers in the world where you could create this host table, the IP address and the name, and then you could call it by name. Got a little bit beyond that. That's why we had to get DNS in order to do that. The private IP addresses, the ranges were the 10 range, the 172.16 to 172.32, doesn't include the 32. 32 is the next network, and then the 192.168 range. And those are the addresses that we can use on our network without buying public addresses. They're not routable on the internet. And then we talked about the sliding window. Did the demo, and again, if you want to look at that, the sliding window is we have X amount of data. We have a window that we send, and the windows are negotiated. The window sizes are negotiated whenever we start the system. And I want to try to do something here. The window size, instead of doing every packet, we're going to break these windows out, this one at least, up into packets. And you saw that with the ABCD. And we move along, we send the data, and the data gets acknowledged. Once the data is acknowledged, we can move to the next window. That is a TCP sort of arrangement to be sure, with the acknowledgments, to be sure that the data actually reaches the destination. Connection oriented, and it's sometimes called a reliable protocol. And the reliability comes from this acknowledgement. It doesn't mean that UDP is unreliable, because usually the applications are going to take care of doing it. So the acknowledgement makes it reliable to be sure that everything gets there, the sliding window. Ping, traceroute, and telnet. Ping and traceroute were layer 3, telnet layer 7, or in the TCP model layer 4, the application layer. You can telnet to a port, telnet 192.168.1.1, 80, which will telnet to port 80. You can check to be sure that the application is running there. The variable length subnet mask, we did exactly the same thing as we did when we were subnetting. We used the increment. We just started out with, if we had the first one was 64, then, 64 addresses, our next network was 64. If the next one was 32 addresses, then we went to 96. If the next one were 4 addresses, it would be 100. 6, and then a very small one, 100. So we can better utilize the addresses that we own. Now, do you really need to do this in the world of private IP addresses? Maybe not, because the private IP addresses are free. You use your Class Cs and just go on to the next one. Is what people typically do, because there's a whole lot of them. Cdp Neighbors, I don't recall talking about, but we're going to talk about it, and it's just a show Cdp Neighbors. And what it does is shows you all of the directly connected Cisco devices. It's a Cisco proprietary protocol. There is also one called Lldp, which is an open source one. We'll show you Cisco and everybody else that's directly connected. In other words, if we were on a switch here and we ran it, we had a router and a router, it'll tell us the routers that are directly connected to that device. And if you do detail, it shows you a whole bunch of stuff, like what's the IP address and all sorts of other things. It tells you what kind of a device it is, and I think that we do a little bit more with it later anyway. I will be sure, don't let me forget to be sure to show that one to you. It's a pretty neat thing, but it's also something that say, oh, that's pretty dangerous, because anybody can come in and look that stuff up, and the answer is, yeah, it can be kind of dangerous, but the other answer is Cisco phones need it in order to do that. Lesson 5, IPv6, we talked about it, the 128-bit address, and we used CIDR notation. I'm not going to try to write one, but CIDR notation in order to specify the number of bits in the IP address instead of writing a subnet mask. The shortcuts, we could drop the leading zeros and we could use the : once. Auto configuration, the EUI 64FFFE was the key to that, and that's in the host portion of the address, and then we append the network prefix to that. We had a unicast, a multicast, and an anycast address in IPv6. There is no broadcast in the IPv6 world. Link locals kind of sort of take care of that. DNS and DHCP. DNS, we looked at the lookup process, and you had a bunch of labs on it. A fully qualified domain name to an IP address. Cache uses the hosts table. We cache DNS lookups on the workstation. Windows does. That's the first place it looks. Then it goes to the DNS server. DNS server looks in this cache. If it doesn't, it starts to the root and it goes back to the top level domain and then to the company domain. I think they're called second level domains in proper terminology. And on down until we find an IP address for the computers, we'll say, or for the station, whatever it is. What you're going to see it called is UDP. I said TCP and UDP. I don't want to confuse the situation. There are situations that you use TCP, but we don't talk about it in this class. UDP port 53 for DNS. That becomes important when you start writing ACLs, access control lists, to either let it in or keep it out, whichever way you want to go. DHCP. DHCP was a UDP broadcast, the DORA, the discover, offer, request, and acknowledge. And we had the relay agent so that we could have a centralized, if we had a DHCP server down here and we have a router here and we have maybe a network 1 here and we have a network 2 here and a network 3 here, we can consolidate, centrally manage DHCP and create a relay agent here with the IP helper command in order to manage them. Centrally only have one DHCP server instead of having to have a DHCP server on every one of our networks, which could get kind of expensive, although you could do it with money. If you're running Active Directory, though, I think that you guys that have done that, it works a whole lot better with its own DHCP server than it does with a Linux server. NTP, Network Time Protocol, Application Layer Protocol, port 123, we talked about stratum, how far are you away, how far down the line. The reason that becomes significant is for delay. Because there's going to be a little bit of delay. Not anything that you and I would notice, but there is some delay. And you can see that when you go to the internet. It goes pretty darn fast. If you go to get, the Washington Post from Denver, it pops up pretty quickly. And then in there we had the time masters and the time clients. The time masters sent time to the time clients, and they're going to go out to probably a stratum 1, we hope, time source in order to synchronize it so it's very, very accurate, and then it sends the accurate time to the time clients. ARP, IP address to MAC address, and we use the MAC to get to the device because it is the permanent address, the fixed address, the BIA, the burned in address in Cisco parlance, set by the manufacturer. Yeah, I know there are softwares that you can actually, on Windows, all you got to do is tell it's a different Mac, but not a good idea because if you have duplicate Macs, having done that once, it just confuses everything because sometimes it goes to the right place and sometimes it goes to the wrong place, and you never know which one it's going to because it depends on which MAC address is in the ARP cache on it. And the MAC we use for final delivery of the devices. Network address to get to the individual networks. Routers find networks, MAC addresses find machines. And that's it. Let me stop this